So I'll start with my background, who I am and why I'm here banging on about soils. Then I'll go into the overarching soil properties, so try and break it up and make a bit more sense of it, and different soil sampling strategies you can use with precision ag. So that's me. I've always been really passionate about the field of soil science. I can't really tell you why. I grew up on a farm and just always was really intrigued with what's happening under where the crop's growing more so than above. So a fifth generation on our farm between Jamestown and Peterborough, so just in from Goyder's line. I now live on my partner's farm, which coincidentally is also in the Ongala area, where I help out as much as I can. I studied a Bachelor of Ag Science, followed by honours in Advanced Soil Science at University of Adelaide. So in my honours project I looked at pH mapping using different sensors to hopefully reduce the costs to the grower of collecting that type of data. So that was all using spectral stuff. Now I work as an agronomist and soil consultant with elders in Jamestown. So last year I started doing my fee-for-service soil consultancy just because I suppose I saw a gap in the market. I wanted to help make sense of all these different maps. Lots of people have huge amounts of data on their computer, and I felt that the crossover between my agronomy and my soil science was really useful in trying to interpret that. Growing my book with soil consultancy fairly quickly at the moment, which is great because that's what I really enjoy doing. And I'm also part of the Up North Farming Systems Committee, which I suppose is part of the reason why I'm here. So when I start thinking about soils, I try to break it up into three different categories. So there's the chemical stuff, so pH, which we've talked a little bit about, which a lot of people are familiar with. Salts, so sodium, magnesium, all the different salts in the profile, and nutrient holding capacity, which I talked a lot about just then, so the CEC. Then there's the physical, so soil structure, which you'll hear a lot about, the presence of coarse fragments. So when I'm saying coarse fragments, I'm really just talking about anything that's larger than the size of a sand granule. So it could be gravel that's inert, so have no chemical charge at all. It could be limestone that does have a charge and can play havoc on your nutrients. So anything greater than sand particle. So then you've got your soil texture, so your clay, silt, sand, and the water infiltration ability. So that has an influence on erosion and directly links back to the compaction piece. And then lastly, biological. So your macrofauna, so earthworms, anything you can see with the naked eye. Your microfauna, so bacteria and microbes, things you can't see. Your roots are actually a part of that category, so your plant roots, and organic matter as well. Organic matter is over there because that actually acts as the energy source for all of the things above, excluding roots. That's why that's in that category. So I'll start with pH because everyone's relatively comfortable with pH. You've heard a fair bit about it. So it operates on a spectrum as well. So at the top you've got your alkalinity. So anything above a pH of 7 is considered alkaline. And then at 7 you've got neutral, and below that you've got acid. And obviously the lower that goes, the more concerned you get, and the higher that goes, the more concerned you get. In literature they recommend a pH of 6.5. That's the point at which your plant nutrients are most available, but before toxicities start to come into play. So I suppose the reason pH is important is because it does change the availability of nutrition. So if you've got an alkaline soil, that means you've got reduced availability of your phosphorus, which is a macronutrient, nitrogen, another macro, and then your copper, zinc, manganese, iron, and calcium. You've also got potential toxicity, so that just means excess amounts of, or excess availability of boron. And then at the acid end, you've got reduced availability again of nitrogen, potassium, sulfur, all macros, and then your calcium, magnesium, and molybdenum, and potential toxicity again of boron and aluminium this time too. So that is essentially shown in this picture here. So this is pretty common. I'd say you've probably seen it before, but it's just showing. So red is where it's not available, yellow where it's becoming more available, and green where it's at its most available. So if, you look up here, it's all either in green or yellow. Another reason pH can be important is when you're thinking of your rhizobia. So when you've got your legume rotation, they really hate acidic conditions, and so you'll get reduced nodulation, reduced nitrogen fixation there too. Then you've got your soil salinity and acidicity. So this is probably the next most common thing that people talk about. So slaking and dispersion are the in-field tests you can do to essentially identify these. So slaking up here is essentially where you've got your aggregate, which is just a clump of soil, and it's just fallen apart. So once you've added it to water, you'll see a lot of bubbling, and it will essentially just crumble and collapse. And that's because the water isn't able to get into the particle quicker. The water that is going into the particle is providing so much pressure to all those different particles, they're just crumbling. And then alternatively, you've got dispersion. So that's this milkiness. A lot of people will call it, they'll say, I've got a soupy soil. So you'll see in seeding time, you'll sow your paddock, you'll get your opening rains and it'll go soupy. And then once it's dried out, it'll crust over and it'll be cracked. So then that leads to poor establishment because plants have to push through that barrier before they can establish. So they've already exerted a lot of energy that they've got in that seed, and it'll delay emergence. So in the colder areas where it gets really cold really quick, if they've struggled to get out of the ground and maybe they've taken 3 or 4 extra days to get up and they've used a lot of that energy, that'll actually delay them a lot because once they've got out then it's cold and so their growing conditions are less than ideal. They'll go really slow and they'll be behind for the rest of the season. So that's caused potentially by acidicity in the topsoil. That's just one example. There's also subsoil acidicity as well. But yeah, it's shown by this dispersion here. So essentially what's happening, the cause is sodium, which is one particular salt. It can actually bind to what I was calling the CEC of the soil. So it's taking a position on the soil, and when water is introduced, each sodium particle on each different site of the clay or organic matter, it's repelling one another. So sodium doesn't want to be close to one another, so it's repelling and it's becoming suspended in solution then. So that's what's happening there. So this is sort of what I was talking about before. The 3 different measurements that I'm considering when I'm getting my chemical analysis or a soil test back from the lab. So first I'll look at electrical conductivity, EC. So that'll either be EC 1 to 5. So that's essentially the test that comes straight from the lab. 1 to 5 just means 1 part soil, 5 parts water. So it's just put in, test tube shaken and measured with an electrode, and that's the raw result you're getting back. And that's looking at total salts in solution. Alternatively, you've got your ECSE. So that's actually looking at your total salts compared to your soil texture. So because sodium can only bind to the clay particles, the less clay particles you have in your soil, the less of a problem you've got. Alternatively, the more clay particles, the less salt you need to then have a problem. So that's when you go down to the exchangeable sodium percentage, your ESP. That's looking purely at your sodium cations, or sodium cation percent in your soil. So that's the percentage of sodium compared to all the other cations. So I'll measure all the other cations and get a percent of each. So that's when you start looking at your ratios of how much you want of each. And then you've got your electrochemical stability index. So not all labs will actually do this one for you. You can calculate it out using other things on the soil test. And that's essentially looking at this divided by this times out by your texture factor. And so a lot of soils through void align, because they're so heavy in clay, they don't need a lot of salt before you've got a problem. So that's where you'll want your maintenance line. So electrostability index, induced dispersion, that's where you've got low organic carbon but lots of clay and only a little bit of salts, and you'll need just a maintenance gypsum. So half a tonne every 5 years incorporated into your rotation. Alternatively, you can have magnesium-induced dispersion. So unfortunately, gypsum won't fix that because it's not actually going into the soil like sodium is. It's just sitting there in the profile. So the only real thing you can do there is increase your organic carbon. So organic carbon is essentially the glue of the soil. So it'll hold your soil together and create structure. So the more of that you've got, the more resilient a soil is to dispersion as well. So that's why there's a huge amount of projects at the moment looking at how to increase organic carbon economically.
What else does magnesium do? Because I've got a couple of soils that are deficient in magnesium, but no one's ever really told me.
Deficient, so it's a micronutrient, so it's needed in trace amounts for your plant. But yeah, it depends. Without looking at a soil test, it's probably not what I would call a low-hanging fruit. It's one of those micronutrients that could potentially increase your yielding capacity, but only if you've got all your macros in check, only if you've got your pH in check, and only if you're getting the rainfall to get up to that yield where magnesium would make a difference.
Yeah.
So it's good probably to have less of it than more of it, because it'll become more problematic having more than having not enough, if you know what I mean.
Does it play a role in phosphorus availability? Is there a link there?
Not that I'm aware of.
No.
Maybe, but like the same thing again. I think probably carbonate would be a bigger limiting factor than magnesium. I'm always trying to, I guess what I'm trying to do is look at the big picture instead of honing down on some small factors that might boost yield by 0.01%. I'm trying to get we've done the 10%ers by stopping cultivation and starting with like Roundup and that type of thing, and we've got our variety chosen so that we've got our best variety and our best genetics. We've got our spray program under control. If we fix pH, then you're sort of looking at your 1%ers at that point, or purchasing more land essentially. That's, yeah, I sort of try not to get too tied up in the 0.01s, because that's when you start forgetting about your other stuff, because you spend so much time to get this 0.01% under control that you don't have time to get your big percenters. So yeah, I tried big picture stuff, I suppose.
Just curious, because it's one of the things in one of that box that always comes in low and nothing's ever said about it. It was just curious.
It's interesting also, if you compare thresholds between labs, they're different. So we go through nutrient advantage and you can select, like if your paddock's going into wheat, you can select either a wheat at a 1, 2, 2.5, 3, 3.5 or 4 tonne. And then with those, you've also got your PBI, so your phosphorus buffering index. And all those different thresholds will be different depending on what I'm choosing. Or if you go to APR, I haven't done that for a long time. I don't know if you know what the thresholds can you choose for wheat versus barley versus canola.
Crop type in it does.
Crop type and what yield.
Yeah, okay. So those thresholds will all change as well. It depends what the person's chosen. Might not be consistent depending on what point at the rotation the soil sample. But even if you compare parallel APR to nutrient advantage, they're also slightly different based on, because it's all independent testing to get the thresholds, it's also slightly different. So I'm not sure what threshold that would be coming back under.
Yeah, sorry, that is probably on our soil tests we've had done.
Yeah.
This particular block is consistently lower than any of the values that we see on
comparatively
comparatively
rest of your
across.
paddocks.
the rest of the farm.
Yeah.
But the yield's quite, it's not something that concerns me because it
Yeah.
yields, but it's, you were talking about magnesium, so I thought I'd ask a question.
No, that's fine, yeah.
There are areas, I know on the EP, that a lot of magnesium is going out more and more. Speaking to Tech there a couple of weeks ago, and they have more magnesium going out. No, sorry. Yeah, magnesium going out than manganese now. So I don't know if that plays a role with when you do have your high calcium percentage. You sometimes have low magnesium percentage in cattlemen's there, so that ratio's out. So your plant could be deficient. So potentially trialing something there, but there seems to be more and more going out magnesium. I haven't ever played around with it, so but I know I have soils that come back low.
So, this is more talking about excess rather than not enough, because magnesium is essentially present as a salt, so excess will cause issues. So then the next type of dispersion is sodium, which I've already touched on. So that's where you do apply the gypsum. So that's essentially a two-step process. So you'll put the gypsum out, it'll leach down, and essentially take the spot on the cation exchange capacity where the sodium was, leaving the sodium free in the soil solution. And then once it rains, that leaches the sodium down. So that's why you need gypsum when you've got sodium, but you don't need it when you've got magnesium, because the magnesium isn't actually bound to anything, it's free and able to leach at any point, whereas the sodium's bound, and so you need to first of all detach that and then allow it to leach. And then the last one is you can also have sodium and magnesium induced dispersion. So that's where you've got excess of both salts, and so that's where you apply the gypsum to get rid of the sodium, and you hope for a high rainfall year essentially to get rid of the magnesium. So that essentially is a problem in the lower rainfall areas because there isn't that constant rainfall to leach those salts out. In the higher years, it's more, there's too much leaching and so you've lost your nutrients. Cation exchange capacity. So I've touched on this a fair bit. Just tried to put it into one sentence to summarise what it is. So it's essentially how well the nutrition in the positive cationic form can be held in soil, and it's directly dependent on clay percentage and organic matter content of the soil. So clay and organic matter have negative charges, and so therefore are able to bind positive nutrients onto the sites and essentially stop them from leaching beyond the plant root zone. So that's it in a nutshell, and that's why you want a nice clay percent in your soil, and if you don't have that, the next best thing is essentially getting that organic carbon up in your soils, and that's what we're trying to do at Burrito. So just again tried to make a bit of a graphic to explain what I'm saying. So clay and organic matter particles are smaller in size compared to sands, however they have a lot more charge. So you can essentially see here I've put on a heap of different positively charged elements around the clay or organic matter, which has a CEC of 25. Then you move over to a sandy loam textured soil or a sand particle, it has a CEC of 5, and so therefore it only has the 5 on here. And you can see the spectrum along the bottom. So sand ranges in the CEC of 0 to 8, and then it goes right up to clay. So if you've got a pure clay soil, that'll have a CEC of 40 plus. And so it essentially can hold a lot more things. The next is soil structure. So essentially, there's two categories I've split it all into, what you want and what you don't want. So it doesn't really matter what type of structure you have, as long as there is a structure, then that's a really positive thing. So when I'm talking about structure, essentially I'm talking about the presence of something that the roots can follow down into, or something that makes the rooting depth easy. So where that isn't is essentially called structureless. So you've got your massive structure, which is essentially a clay textured soil, and it's just like hitting a brick. It's just really hard to get anything down into it. So that's where potentially ripping is an option, or the use of tap-rooted species, because they can exert more pressure to get down into that. They then create the biochannels for your fibrous roots to go down the next year. Or you've got your single grain type structuralist, so that's like when you go to the beach, that's a structuralist soil, because you can pick it up and you can see the single grains. There's no cohesion between the grains creating structure, it's all just single grained.
So Beth, with that, is that where I took on some share farming country a few years ago, and I went onto it, and it gets run pretty hard with sheep, and there were clods out there, and I'd pick up a clod, and I could not break it apart. And I thought, because we took, that was in those couple of bad drought years, and then I went just to double check back on that place, so I picked up similar, and you could squeeze it and it fell apart. That's the difference you're talking about?
Yeah, it is, yep. The only thing there is, so as the
and they're side by side paddocks, so there's a main road in between the two, so it's...
Yeah, so as soil dries out, it means that the structure essentially becomes stronger or harder to break, and then as it becomes wetter, it's easier to break. So that's why you'll hear a lot of people, if you're early in your, like if you want to do controlled traffic farming, everyone says the first thing you should do is your boom spray, and that's because it's going over your soil at its wettest, and so that's also at its most vulnerable to compaction, because as it gets wetter, it'll compact a lot more, it'll lose structure. So it sort of sounded like you were doing that at its driest, which means it would have had its, it would have been harder to break than if it was wetter.
Yeah.
But yeah, it does sound like a bit of.
But it was, they were side by side, so it was the same day, I went from one side of the road to the other.
Yeah. Yeah.
And things happened later on in that year that sort of makes sense with what you were saying there, that not the organic carbon in it.
Yeah. So essentially with all of this stuff, what we're trying to do is optimise rooting depth, because the deeper your roots are, the more resources they can get. So with compaction or any other subsoil toxicity, we're trying to correct it so the roots can get down. So with compaction, it's really bad because they have to exert more pressure to not get anywhere near as far as if it was a good structure. So they're already stressed because they can't get down, and you'll look at roots in a compacted soil and they'll actually be torn apart. Like you'll look at the coating of the root on the outside of the rhizosphere, and it's actually really torn apart. It's really prone to being attacked by pathogens in the soil, and yeah, it just can't get resources. So yeah, compaction is really silent, I suppose, but a big one. Even just compaction pans as well from like previous tillage practices. But yeah, I suppose the only other thing to touch on there is how to work out if you do or don't have structure. So Upper North does have a penetrometer from a previous project. The only problem there is it only works if your soil's at field capacity. Rarely do we get enough rain to get to field capacity, but you can like put a drum out and fill it to get it to field capacity, then go out and measure. And essentially the deeper the penetrometer can go, the better your structure. Beyond that, it's a soil pit, I suppose, which is obviously pretty invasive and not everyone has an excavator. But yeah, like with the cores that we do, it tells us a little bit, but because you're compacting it by taking it, it's hard to draw on structure there. But that's why I do say look at rooting depth when you take your cores, because if the roots all of a sudden stop, then it's a potential indicator of compaction or something else. So yeah, that directly leads also to water infiltration and holding capacity. So a good soil structure, it'll be really high in either clay content or organic matter carbon or both. It'll have limited dispersion because, as I said before, that will result in compaction when it dries out again, and it'll have no coarse fragments. So another thing to consider when you're looking at your soil structure and water holding capacity is the presence of coarse fragments. So the room that any rock or gravel is taking up in your soil is room that water can't go, essentially. So I know a few people have wanted to calculate out their soil's water holding capacity to then calculate out yield, to then calculate out nitrogen requirements. And I've seen a few people just forget to consider coarse fragments, because that does actually have a really big impact on how much water your soil can hold. So then comparing good structure to poor structure, so often there's really low clay content and organic matter content. It could be dispersive, have lots of coarse fragments, or be compacted from livestock or machinery over time. And then I suppose the last thing to touch on is the soil biology sector or segment of soils. So macrofauna, that's your larger biology that you can see with the naked eye, earthworms, earwigs, dung beetles, and they essentially complete the initial step for the decomposition process. So they essentially make the stubble, for example, small enough for the fauna to then get at it and break it down to those original nutrient elements. So then you go to your microfauna, they're really small and unable to be seen with the naked eye, and they complete the last steps of decomposition. So their energy source is organic carbon. So the less organic carbon in your soil, the less ability they have to then cycle your nutrients through the soil and back into the next crop. So they're responsible for mineralisation of nitrogen, just as one example that we're all familiar with. The next category, I suppose, is fungi. So they can either be positive, so symbiotic, or negative, antagonistic. So a symbiotic example is mycorrhizae or rhizobia, and an antagonistic example is rhizoctonia. And then last is plant roots. So you either have fibrous plant roots like on your cereals, so they're unable to exert as much pressure as a taproot, for example, like a canola plant or a legume. So I suppose that's all I was going to touch on with soils, unless there's any other questions. No, easy. So now I was just going to quickly go through some different sampling strategies, just to give you the different options and the pros and cons for each. So the first would be the traditional aggregated soil sample, just in a transect across the paddy, just go in the gate, pretty much straight down the guts of it, mix them all together, and then you essentially get one lot of results for the whole paddock. Obviously you're unable to identify variability in this way because you've mixed it all and it's an averaged result, but it is the cheapest option. Then next, I suppose going along the lines of increasing the ability to identify variability would be a zoned aggregated soil sample. So in this method, I suppose you'd be zoning the paddock using some sort of data like a yield map or even better, numerous years of yield maps to create zones, and then you'd be aggregating zones per paddock. So in this example, you would get 3 sets of results for the one paddock, which would then enable you to go on and complete VR maps. So obviously it's a little bit more expensive, but there would still be scope to get comprehensive tests for each zone in there because there's only 3 per paddock. Then the next would be going to a grid sample. So this is what Rory does a fair bit of. It's sampling following some sort of grid. So whether it's a 1 hectare grid, so every 100 metres, or it could be even more regular again. But that's where each sample is treated individually and tested, and you get the grid to then stitch it together and create a high-res map at the end. So typically, because there's so many samples per paddock, you're only really going to focus on maybe 1 or 2 constraints under this sampling method, so it won't be comprehensive like the first 2, but it'll be higher res for those 2 constraints that you're looking at. So this is how a lot of pH maps are done now. Moving on from the VARIS. The next is soil sensing using swath widths. So that's what you'll do when you're in your header. At harvest time, it's constantly collecting data, and then you stitch those widths together to make a full map. And another example of that is your EM sensors. And then the last one, which I do a lot of, is ground truthing cores. So they're educated cores, I suppose, using different data layers to go and essentially investigate different zones at a really high resolution per zone. So that you can do your comprehensive soil tests on again. Probably can't create a map from it, but you can certainly use it to figure out what maps you'll need for the overall paddock. So that's all I had for the soil crash course, unless there's any questions.